Welcome to The Explainer. We're going to explore a pretty fascinating paradox today. When we picture the modern digital empire, cloud computing, global networks, massive AI models, we almost always visualize sleek silicon wafers and these ultra-modern neon-lit server farms. But what if I told you that the foundation for all of this wasn't actually built on silicon at all? The architecture of our entire modern world was actually forged inside a dusty 1912 wooden workshop in Palo Alto, California.
I mean, it sounds totally impossible, right? How does a fragile 1912 glass tube lead directly to generative AI? It feels like a massive conceptual leap. But today, we're going to trace an unbroken, continuous mathematical lineage. We're going to follow the path from a very modest inventor's workbench all the way to the complex algorithms that are routing our digital consciousness today. Okay, let's dive right into this.
Section 1. Mechanical Wall, Friction's Limit. Back in the opening decade of the 20th century, the technological status quo was, well, incredibly heavy. Power was all about the physical friction of mechanical and heavy electrical machinery. We're talking massive steam turbines and traditional copper wire telegraphy. If an electrical signal got weak over a long geographic distance, humanity had absolutely no sophisticated way to rejuvenate it. We could passively transfer electrical current, sure, but we couldn't delicately control it. We had literally hit a physical wall.
Which brings us to the crucial shift that changed absolutely everything: electronic engineering. This isn't just about moving big currents around. It's the practice of using a tiny, low-power electrical charge to precisely gate, manipulate, and accelerate an independent, high-power stream of electrons. This was a monumental leap from brute force electrical engineering to nuanced active control. For the very first time, humanity could actively multiply power. And honestly, grasping this shift is the absolute key to understanding why our modern devices can process information at all.
Moving on to Section 2, the defective valve. Enter Lee DeForest. By 1911, DeForest is fleeing a chaotic, frankly messy web of corporate bankruptcies and patent litigation on the East Coast. Desperate for a fresh start and honestly probably a hideout, he arrives at the Federal Telegraph Company in California. And he brings with him an invention that is undeniably brilliant, but at this stage deeply, deeply flawed.
The technological contrast here is just stark. Think about the 1904 Fleming diode valve. It was completely passive, just two elements, a filament and a plate, doing the basic job of converting alternating current to direct. But DeForest, he simply inserted a third element, a tiny platinum wire grid right between them to create the Audion triode. By doing this, he completely transformed a passive device into an active voltage gate. Now, at first, DeForest didn't totally understand his own physics, and his early vacuum tubes were choked with gas, totally unstable, and, constantly burning out. But despite the explosions, the fundamental physical architecture for modern amplification was born.
Section 3. Cascading, linking the audience. Let's zoom in on the summer of 1912. Inside a quiet workshop at 913 Emerson Street in Palo Alto, DeForest is working alongside two really brilliant engineers, Charles Logwood and Herbert Van Etten. Together, they make a critical conceptual leap. They figure out how to stop treating the Audion tube as an isolated standalone component. Instead, they asked a simple question: what if we link them together?
They decided to wire 3 of these Audion tubes together in a serial, cascading sequence. So the amplified output of the first tube fed directly into the control grid of the second, and so on. To test this revolutionary new circuit, Van Etten placed a standard telephone microphone near a piece of paper on the workbench. He simply tapped a pencil on it. And incredibly, they even let a live housefly walk right across the paper. Just think about how completely absurd and incredibly faint that physical input is. A literal housefly walking on paper.
But the result? Unbelievable. Through the headphones, that incredibly faint pencil scratch sounded like a deafening metallic crash. And the tiny, almost silent footsteps of that housefly, they vibrated through the system like the heavy thud of marching combat boots. This cascading architecture took those nearly imperceptible sounds and multiplied them exponentially. They had literally converted an abstract tiny electrical current into massive, high-velocity acoustic power. And they weren't even done. Just a few weeks later, they were experimenting and accidentally routed the amplified output energy back into the tube's own input grid. Instantly, the system produced a clear, sustained, high-frequency acoustic scream. This was the accidental discovery of regeneration and oscillation. It proved that this amplifier could also generate continuous radio waves. Practically overnight, they permanently eliminated the need for those massive, multi-ton mechanical generators just to send radio signals, a real game changer.
All right, Section 4, Transcontinental Link. AT&T scales up. We now shift into the commercialization phase. DeForest knew he had an absolute gold mine of intellectual property on his hands, and the corporate giant most desperate for this exact technology was AT&T. They wanted to build a transcontinental telephone line, but they were staring down an impossible physical barrier trying to connect the East and West coasts.
AT&T had a massive signal attenuation problem. They could pump a strong voice current in from New York, but because of miles and miles of resistive wire, by the time it reached Colorado, it was reduced to a dying whisper. It didn't matter how much current started in New York, the physical resistance just drained it. They desperately needed a localized midpoint amplifier that could intercept and re-energize that dying whisper before sending it on to San Francisco. DeForest's cascading triode was the exact solution to this geographical nightmare.
So AT&T bought the exclusive wire communication patent rights from DeForest for an initial $50,000. Their physicist, H.D. Arnold, identified DeForest's soft vacuum flaw and immediately engineered a pristine, hard high vacuum so the tubes could actually handle enterprise-scale voltages without exploding. The result of all this? A staggering 3,400 miles. On January 25, 1915, Alexander Graham Bell successfully spoke across 3,400 miles of wire to Thomas Watson. Just like that, the mechanical isolation of the West Coast was officially over.
Section 5. The SV Blueprint, Codifying Innovation. The structural narrative of 913 Emerson Street wasn't just about building better radios. It actually codified the exact, repeatable methodology of Silicon Valley. Long before there were modern software startups or app developers, this team established the literal playbook that would shape global tech development for a century.
And here is that exact, repeatable pipeline. First, a hyper-local talent concentration, pulling really sharp interdisciplinary minds from nearby Stanford and putting them in a collaborative, unsiloed workshop. Second, the shift from component to systemic modularity, realizing that linking things together as a platform is where the real power is. Third, the rapid monetization of abstract IP, selling those patents to a giant with scaling infrastructure. And finally, plugging that tech into a global platform monopoly to change the world, recycling the capital right back into the local ecosystem.
Which brings us to our final act today, Section 6, Vacuum Tubes to AI, the Continuum. This is the ultimate payoff of our explainer. We're now going to trace the direct, unbroken line from that fragile 1912 glass valve straight into the cognitive software landscapes of modern artificial intelligence.
When you follow this technological continuum, the physical evolution is just staggering. We start with the 1912 Emerson Street triode. Fast forward to 1947, and Bell Labs invents the solid-state transistor, replacing the hot glass bulb with a tiny block of silicon. By the 1950s, Intel is printing millions of these onto integrated microchips. And today, we have massive arrays powering generative AI. While the physical chassis shrunk from a bulky, hot, explosive glass bulb to a microscopic sliver of silicon, the fundamental logic, using a small, low-power current to gate and control a separate high-power stream, has remained exactly the same.
Just think about the massive scale of today's endless computational matrix. Consider the way data flows through the hidden layers of a modern neural network, like the massive models built by OpenAI or Anthropic, running on billions of microscopic NVIDIA GPU transistors. The mathematical output of one computational node is weighted and fed directly into the input of the next to generate a complex automated thought. Sound familiar? That layered inference is the direct digital manifestation of Logwood and Van Etten's cascading workbench circuit from 1912.
Ultimately, the story of 913 Emerson Street is a monument to our capacity to capture the invisible abstractions of science. By breaking the tyranny of mechanical friction, humanity learned how to build tools out of pure electrical energy. We learned how to capture, amplify, and route our very consciousness, forging pure physics into the permanent institutional architecture of the modern world. It's an absolutely breathtaking leap in human capability. So I'm going to leave you with this final, provocative thought to ponder. If the core logic hasn't actually changed in over a century, are we really building new minds today? Or are we just finding faster, more microscopic ways to arrange the glass and wire of 1912? Every single time you interface with an AI or route data through the cloud, the algorithmic magic we rely on is still echoing the cascading power unleashed in a small Palo Alto workshop over 100 years ago. Thanks for joining me on this explainer. See you next time.